Hi, everyone. I think we're connected.
Good morning.
Maybe there we go. All right, thanks. Okay, so is there anything we need to go over before diving in? I think I'm unmuted now. Can everybody hear me okay? All right, sounds like it should be having problems. All right, so today we're going to finish up talking about attention, at least as kind of its own topic. You know, as we've been talking about before. Okay, good. Yeah, now the audio's back. So all these other topics that we discuss, especially laboratory studies where you ask a subject, okay, I want you to do this. We're studying attention, whether we point it out or not. So we're going to be moving on towards talking about memory later in the week. As part of that, we're also still going to be thinking about attention, right? So and as we mentioned before, you know, this class is cumulative in the sense that you're becoming experts in this area, and all the various topics that we study for convenience, you know, on their own, perception, attention, and so on, they really all relate to one another. So I think with some of the topics in memory, we're going to make this point pretty hard, in that a lot of the memory effects are byproducts of attention effects. So stay tuned for all that. But today, so I thought we could start with something that I'm very happy about. Let me do this share screen. And I was going to look up the person who sent me this article. Remember last time we talked about somebody asked a question or had an observation about binocular rivalry, right? And that's making a great connection back to perception that we talked about several weeks ago. And the question is, let me try to, here we go, get this going. So the question was, well, what about people with hemineglect? Might they have differences in binocular rivalry? And she sent me the paper, and I looked at it, I thought it was a good paper. And as I read through it and started thinking about this, it was even more instructive, I think, for what we're trying to get out of the class. So note here that the student, I'm sorry, I can't remember exactly who you are. If you want to say so, jump in. If not, we'll just kind of go. That she came up with an idea that professional scientists came up with. And we know that because Wall et al. Published in a good journal, is in Brain and Cognition, which is a good journal. It's not the top one in the field, but it's certainly respected and has very solid research in it. So the point I want to make to every one of you is that you guys can, when you think about the topics in this course and what we discuss, your ideas are in the ring of scientific ideas. You know, they can compete with the professionals. That's not to say that you'll have the background that somebody that's been studying this stuff for a decade would have, but your thoughts matter, and they can often be very insightful. And so I thought this one thought that the student had was obviously very insightful, because other professional scientists had that same thought, and they went to the trouble of running an experiment to test that idea. So I guess I'm just trying to say that this should be an encouragement that you guys can do this, and that, you know, that I would like, that's one of the main things I want you to get out of this course, is the confidence to be able to ask questions, and the confidence that your analysis can be really insightful and good and important. All right, and this is objective. I'm not just kind of saying, oh, this is, you're great because you're great. I'm saying this is objectively, she had a good idea, and it's in the research literature done by professionals. So, you know, I'm really proud of her for that. All right, so let's get at kind of the actual experiment. So the question was, well, we've got this right hemisphere damage, and we've been talking about all these different effects on attention, whether it's stimulus processing, or whether it's even just attention to your mind's eye memory of a square, or whether stimuli are close to you or farther away from you. There are all these kind of high-level attention deficits. So what about this perceptual phenomenon of binocular rivalry? And just to refresh everybody's memory, if you pick two stimuli to each eye separately, so you wear goggles and you could have two pictures, one to each eye, what you get is not a superimposition of both pictures. What you perceive is you'll perceive one of those pictures well for a time, several seconds, and then it will kind of fade away, and then the other picture to the other eye will be what you're perceiving for a while. And then that kind of fades away. So you get this back and forth perception that goes from what's presented to the right eye to the left eye. So that's binocular rivalry. For laboratory studies, you can be more rigorous about this and use gratings. That's what we're looking at here. Let me get the laser pointer. That's what we're looking at here. That's just a more rigorous way of going in and studying visual processing, because you can do a lot of psychophysical analyses with gratings if you want. All right. In this experiment, they did that in, I didn't write down the sample, but there were 26 people with right hemisphere lesions. And some of them, they had various degrees, as we'll see, some of them had various degrees of neglect, from hardly any neglect symptoms all the way to large problems with neglect. And then there was a control group, also 26. They were about the same age, and usually you try to control for male, female, but this one they were off a little bit on that. I don't think it was a major factor in the results. And then they also compared high-level visual processing, houses and faces. So remember we talked about the fusiform face area, this area in the ventral stream that seems to be very responsive when you present pictures of faces relative to other types of pictures. And then there's another area, the parietal place, the parahippocampal place area that responds to houses. So that they capitalize on this kind of high level categories of visual things that's farther in the ventral stream versus lower level, more simple visual information that's more the purview of primary visual cortex and secondary visual cortex. All right. And so the first question was, well, does the brain damage in the right hemisphere slow down this rate of alternation? And if so, does that relate to the neglect symptoms? That's really the strongest case you would make, right? Because if you just have brain damage overall, you could say, well, all right, this alternation between left and right, it's messing up high level or visual perception in general. But if it correlates with the symptoms, then you're in a stronger position of saying maybe the symptoms of neglect are an important factor, or at least correlated to this alternation rate that we've been talking about between the eyes. And so they measured neglect symptoms with a test called the behavioral inattention test. So that includes things like what we talked about the other day with the line bisection task, right? And if you ask somebody to scratch a line in the middle, or use a pencil to scratch a line in the middle show where the middle of the line is, people with neglect will move far to the right. And the farther they move to the right, the worse the neglect. All right, so I think that's all the background that we need to appreciate what we're looking at here. So sure enough, Wall et al., as well as your classmate, were spot on that the rate of binocular rivalry, so how long does the percept stay with one eye stimulus before it switches to the next one? For the patients, you've got that alternations are a lot slower. And then you've got with the controls, the alternation rate was a lot faster. So with the patients, the percept tended to stick around longer for one eye before it switched over to the other eye. So the lesions didn't knock out binocular rivalry overall. So it's not as if there was some eye effect or alternation effect, but it really did slow this down. And shown over here on the right, there's a correlation between this bit score. And so the smaller the numbers, the worse the neglect, the bigger numbers, the better off they were. Showed, it was a reasonable correlation. Note here that there were a couple of people that were just alternating super fast that kind of threw off this correlation a little bit. So this is one reason why I always like to see a plot of what's being correlated, because if you just have the number, it can be misleading. This is a little tip as far as reading these journal articles. It's usually, you only get part of the story if they just say the R value is whatever. Let's see. Okay, so there we go. So the hypothesis was, supported with this data. And it's interesting that it relates to the symptom severity. One other thing that I didn't plan on this, but just found as I was reading the paper, that it's instructive as far as how science operates. And as somebody who's kind of, on the front lines with all this, I'm consistently impressed at the type of people that are in science and the honesty that's pervasive in science. There's always a bad apple here and there, but for the most part, it's a very honest profession. And you guys would feel good if you were on the inside, and some of you may want to. I'd encourage you to get into science. It's a wonderful, wonderful field. So they published something called the Corrigodendum, rather, about a year after this. And the reason was that some of their values in the paper in 2017 were incorrect, so that they added a few things up wrong. And instead of just kind of letting it lie, because people wouldn't know, this is their data, so especially if the data wasn't uploaded online, people wouldn't know about this, but they knew about it, and their ethics are important. So what they did was they contacted the publishers and said, we made a mistake. We want to publish this article, this Corrigodendum, to correct that. So people who read our article will get the precise information. And that's what they did. So the new values are in this 2018 publication. It didn't change the outcomes, it didn't change the conclusions or anything, but nonetheless, it's just part of that transparency in science. And nowadays, it's getting even more and more transparent, which I think is a good thing for all of us. All right, so are there any questions about this study? All right, so let's move on. And so we're going to finish up by talking about just a couple other aspects to really flesh out this idea of these attentional deficits, these high-level attention deficits that we see in these hemineglect patients. And then we're going to switch over to another related problem, which is called Balint syndrome. And then we're going to do some functional imaging studies and EEG studies, and then we'll be done for the day. So I think this will actually be a fairly low-key class. I don't think we're going to be rushing towards the end or anything like that, which is good. We can have a break every once in a while from, putting the pedal to the metal. All right. So there's something called the mental number line, and there's a whole field of study around this concept, but it's really very much, it maps onto what you learned as a kid, right? That in kindergarten, they'll have a classroom usually, and it has the numbers all ordered from 1, 2, 3, 4, 5, 6, 7 on a line. So there's a spatial element to numbers, at least in the kindergarten class. And we use this, throughout our lives. Rulers are one example, that sort of thing. But it turns out that the brain may really represent numbers in terms of space. At least that's one way of representing numbers. And so one way that this was shown, which I think was an interesting way, was to have neglect patients do something called a number bisection task. So as you know, let me just go back to the bisection. All right. So here, literally with our line bisection task, you see a line on a sheet of paper or on a computer monitor, and you ask the person to find the midpoint of that line. And like I said a few minutes ago, the patients tend to mark that far to the right. You can do a similar sort of thing, but it's more abstract with numbers. And you can say, what is the midpoint in terms of the range of numbers between two numbers? So what's in between the midpoint of 2 and 6? And with that, you can say 4 is the midpoint of that. And you can score this. You don't give people a lot of time to think about it, by the way. So you give them bigger numbers oftentimes, and they have to answer right away. So they can't just kind of count it out, which you could do if you had lots of time. You just have to kind of give your gut judgment about what the midpoint is. And they score this. So as a simple example, between 2 and 6, you could score the deviation as a 0 if they're spot on and they say 4. And if their estimate is a little low, they say 3 instead of 4. You can score that as a -1, or if it's a 5, you score that as a +1. So that's what we're looking at over here on the y-axis, are these estimates of, what is this deviation from the true midpoint? But in this case, it's midpoint in terms of the range of numbers. All right, so if you do this in healthy control subjects, people who are generally older, matched to the people's age who had the strokes that cause neglect, or control patients, people that have probably suffered a stroke, but it didn't lead to neglect. on average, people are pretty good at figuring out where the midpoint is. I should emphasize this is an average. So there's a lot of variability from trial to trial to trial. Sometimes people overshoot, sometimes they undershoot, but on average, they're pretty good at getting it correct. And you can change the intervals here, three digits in between, 5, 7, or 9. But look what we get with these various patients that have hemineglect. So these are all just the initials of 4 people that suffer brain damage and have hemineglect. That for a small interval, let's say 3, they're pretty good at estimating. If anything, they may be a little bit underestimating that. But then as you get larger and larger intervals, their estimate starts to get more and more towards the bigger number. And that you saw that in all of the patients here. So this is another example of neglect isn't just about sensory information. It's similar to the Piazza study, where they're using their mental, image or their thoughts about numbers. And it may not even be an image in the sense of thinking about it spatially, but it's knowledge, right? It's long-term knowledge. And you get the systematic bias about knowledge of numbers as the task gets more and more difficult, as there's a greater separation between the 2 numbers and you need to find the midpoint of that. So again, just another angle to get it, the idea that this attentional deficit is pretty high level. It's pretty abstract and expresses itself in a lot of sometimes surprising ways. All right, let's move on. So are there any questions about hemineglect? Patients, lesion studies. All right, so we're going to move on and try to get convergent evidence, right? We talked about this ad nauseum, that you don't want to make grand pronouncements about this is the way the brain works based on only one line of evidence. Because each of our methods have pros and cons. Patients, it can give you information about causality, for example. It can give existence proofs that if you damage the brain in such a way, you can get these cognitive functions. And that offers constraints on how we think about how cognition works. And it gives us some sense of parts of the brain that may be particularly important for, let's say, spatial attention, as we've been talking about. But we want to approach it from another angle. So, of course, another angle when we're asking about brain areas, if the question is more spatial in nature, what about right hemisphere areas or parietal lobe areas in attention? Our go-to methodology is functional MRI. And we'll talk a little bit about EEG as well when the questions turn more towards temporal information as far as attention orienting goes. All right, so here's one example. There are lots of studies like this. So I mentioned that the cued attention task, where you have a cue that tells people to shift attention to a location in space, then a target shows up, then you press a button to the target. That's a workhorse paradigm for behavioral studies. It's also a workhorse paradigm for functional imaging studies. So Corbetta et al., they did another one of these studies using a cued attention task in the visual modality. And it's very much like what I showed you earlier with the Posner study. Let me just go back really fast because it builds on this. Let's see even more. Okay, here we go. On this experiment here, right? Where if you present a stimulus, it can be validly cued. The target shows up at the same location as the cue, or invalid. The cue says one location, the target shows up somewhere else. And there are 4 combinations. You can cue to the right, and the valid target is on the right, or the invalid target is on the left, and vice versa. So they did that, but they just had people in the scanner. So they're measuring blood flow, and it can measure it in response to the cues or the targets. And they wanted to know, what about some of these parietal areas that we think are pretty important for orienting spatial attention, because when you have a lesion to that, particularly on the right, you have these disruptions in attention. So this is what we're looking at here in healthy subjects. I don't remember the ages, but most likely they're people that were college students. And what they found was that the blood flow responses to targets, when you sort it based on whether it was an invalid trial and the target was on the left side of space, or the valid trial on the left side of space, invalid or valid on the right side of space, you got an overall effect here where the right inferior parietal lobe, so it's right in that area that if you lesion it tends to lead to neglect, shows this greater response to the invalid trials, which are shown here in red, relative to the valid trials in blue. Right. So the idea here is that maybe this attentional reorienting, you've got attention over, let's say on the right side of space, the target is on the left. Attention is thought to shift to where the location of the target is. You process that better, but it takes a little bit more time, so your reaction time slows down relative to valid trials. And they found that these same areas show greater blood flow. I should mention here this MR frame number. For magnetic resonance imaging, for fMRI, they sample the blood flow only every second or every 2 seconds or so. It depends on the study, but it's on the order of seconds where they get a measure. So unlike EEG, where you can measure every millisecond if you want, or even faster than that, you only have these snapshots of what the blood flow is like approximately every second or two. So these frame numbers are just when those snapshots were taken. So I think here this is most likely about every second or so they sampled this. So you can see how the blood flow response is pretty sluggish. It peaks around 5 or 6 seconds after the stimulus, and then it comes back down. So they found this increase in blood flow response for the right inferior parietal lobule and also the right superior temporal gyrus, which is right next to it. And so the temporal parietal junction, which is like neglect central, if you damage that, it includes a little bit of the superior temporal gyrus as well as inferior parietal lobe. All right, so we got from this down here some convergent evidence, right? We've got lesion studies. If you damage these areas of the brain, you get impairments in attention, oftentimes profound impairments. And if you measure the activity in these areas of the brain when they're not damaged in healthy brains, they show increases in blood flow when you're orienting attention around. So now we're getting our conclusion that these areas of the brain on the right parietal lobe are particularly important for orienting attention. We've got 2 lines of evidence that support that contention. Does that make sense? All right. So shall I move on to Balint syndrome? Okay, boy, everybody's kind of quiet today. No comments before we move on? All right, let's move on to Balint syndrome. And so this is another case study in why scientists should not be naming their phenomenon, because you have these complicated terms that are hard to remember. So we've got for Balint syndrome, especially neurologists, they seem to be even worse than some of the psychologists sometimes, believe it or not. So we've got optic ataxia, optic apraxia, and simultaneous agnosia. So what is optic ataxia? So that's an impairment in visually guided reaching movement. So I've got, here's where the zoom is difficult. All right, I got my cup here. I can look at the cup and then reach for it. That's a visually guided reaching movement. That's really all it is. And we do this without thinking about it. It's part of our everyday lives. You want something, you just kind of grab it. But as we talked about in the context of the dorsal and ventral streams, there's a lot of interactions between the dorsal stream areas and motor areas that's important for coordinating, using visual information in the service of action. And the people with Balint syndrome, that can be impaired. So they would have difficulty reaching for their cup of coffee. Even though they're able to move their hand around, and they're able to, with some qualifications I'm going to talk about in a minute, probably see the cup of coffee, but connecting those 2 pieces of information is oftentimes a problem for them. So that's optic ataxia. Ocular apraxia. So apraxia is just a high-level movement problem. It's actually it's kind of the motor version of agnosias. So remember, with agnosias, you show people simple pictures and they can perceive the visual stimuli, all right, yet they would be unable to or have difficulty naming the pictures. So that's this high-level impairment in visual recognition that's not explainable by low-level impairments in visual perception. Apraxias are like the motor version of that, where it's a high-level motor problem that's not explainable due to basic inabilities to control, let's say, your hands, for example, or in this case, the eyes. So these are people that can move their eyes around. It's not that they have problems necessarily just literally moving the eyes. But if there's a new stimulus, and by new stimulus, it could be like in our visual search experiments that we've talked about a lot, or even the Q target paradigm where they're looking at a monitor and then something shows up on the monitor that's new. Normally, and we don't think about this, our eyes will be attracted to that novel stimulus. In the Q target paradigm, for example, we have to almost make people just focus on a plus sign so their eyes don't naturally reflexively move around to the new stimulus. So this ocular apraxia, people have difficulty having that natural eye movement to it. And when they do, it's kind of, it's not very accurate. Normally when a stimulus suddenly shows up and your eyes are directed towards it, they'll fixate right on the stimulus where it needs to be. These people, their aim will be off and it may move around a bit. So that's ocular apraxia. And the third feature is simultaneous agnosia, which is, I should mention, when we talk about language processing, the error that I just made, I was preparing to say simultaneous agnosia, and the first sound is, and I'm pretty sure when I was saying third, I substituted this part, which I was preparing to make second and added that to the first word. So this is something that's kind of interesting as far as language goes. You're preparing what you're about to say even before you know what you're going to say, which I always think is kind of cool. All right, so simultaneous agnosia, we talked about this a little bit, I think, after that video that we saw at the beginning of the hemineglect portion, where you present two stimuli at the same time, and the person would have trouble attending. They'd only attend to one of those two objects, one of those two things. So you can see this in hemineglect as well, right, where they had the two fingers, they both move at the same time, and the patient would usually just say that the finger on the right side was the one that they saw, and they would not mention the left. However, if you move the left one by itself, then they would say, okay, I see that on the left. So it's not that they couldn't see the stimulus on the left, but the interpretation is there's some sort of attentional competition going on. In the same way that there's competition to spread attention from the right and the left side of space, and the left side loses out in people with neglect, and attention is kind of the default mode is on the right. With simultaneous agnosia, you'll see a similar sort of thing where the default is usually on the right and the left one loses out. All right, so these three features are indicative of Balint syndrome. So if you have hemineglect, you probably will not have optic ataxia or optic apraxia. It's not against the law. There's no law of neurology that says you can't have symptoms in other disorders in one disorder. But generally, if people started having these symptoms of optic ataxia and apraxia and simultaneous agnosia, they'd be most likely diagnosed with Balint syndrome as opposed to hemineglect. So these are different patient categories. And there's an attention angle to this as well. And I should mention, maybe I'll tell you about, so I focused a lot on studying Alzheimer's disease. As far as neurology goes, Alzheimer's disease and something called mild cognitive impairment, which is oftentimes what you get before you have Alzheimer's disease. It's kind of early stage sometimes. And stuttering is what we've been working on a lot lately. But occasionally I'll see other patients as well. And so when I was doing the Alzheimer's work, we had a patient that had Balint syndrome. It was an unusual variant of Alzheimer's disease. So the pathology started not in her temporal lobe, which we're going to talk about on Thursday. That's really important for episodic memory. But the pathology started in the back of her brain near visual areas. And so she ended up presenting with Balint syndrome. And this is somebody who was really, I don't think I can maybe get this all in the Zoom, but in the video that you saw, the neurologists were just kind of moving their fingers like this to demonstrate extinction. I was just kind of wanted to see how far we could push it with this patient. And so literally I was doing that same test. She was sitting in front of me and I told her, okay, just look at my nose and then I'm going to move one finger or the other or both, and you tell me which one moves. And so she's just playing big time extinction as far as just moving your fingers like this. but I was doing it where I would have my left hand basically waving while I was also doing actually I'm doing like this actually from your perspective. So the one on the right was just doing this, and my left side I was literally waving to her. So it was this really salient stimulus. She didn't notice the waving hand. So all it took was just one little finger moving, and then attention was captured by that. And the hand waving, it just, she didn't notice it at all. And she told me that she realized she had a problem when she was driving one day at night, I think. And she said, my visual field, I forgot exactly how she phrased it, contracted. So all I could see were the white lines in the road. She didn't notice trees on either side. This was in California. There could have been a drop off on a mountain on one side. All she saw were the white lines. So you can imagine what that must be like if you're just driving and suddenly your visual field goes down to just the white lines. And she was an artist, and it really impacted her ability to paint. She eventually gave it up because it was too frustrating, because she couldn't have this wide attention. She couldn't attend to a wide range of stimuli in a visual field like we normally do and don't even think about it. So that's an example, kind of a high level example of this attentional phenomena that's usually seen in Balint syndrome, where attention will focus on one object in the visual field. So how can we test this in the lab and do it in a more controlled fashion? So this is one example of doing that. You have your Balint syndrome patient in the lab, and you tell them, I'm just going to show you some dots on the screen. They're sitting in front of a computer monitor, and I just want you to tell me the color of the dots. And so you give them you give them three conditions here. You can have just a bunch of red dots on the screen, in which case they'll say red. As long as they're not colorblind, they'll say it's red, and they'll distinguish that from green. You can use other colors that are not an issue for people being colorblind, just in case you're wondering. Or you can mix them up. You can have red and green. If you mix them up, what you'll typically find is that the patient will only say one color. So on this trial, they may say red. And so we might say, okay, well, maybe now they have this attention bias for red. But if you show them the same scene, let's say a few trials later, they may say green instead. So it's not really a red or a green issue. But it could be about this hypothesis that I just said. What if they're only attending to one of those dots? When everything is red and everything is green, you don't know if they're attending to all the dots or just one dot. But this variability in the mixed color condition suggests, well, maybe we can test that out. So how can you do this? So several experiments, I don't recall who first did this, did something clever. They made a barbell out of this. They connected a line between two dots. And when you do this, now it looks kind of like one thing, right? Like a barbell. Under those conditions, then the patients would say, oh, it's red and green. So that was some of the more compelling piece of evidence that, yeah, maybe they really are just, their subjective sense of what they're attending to is limited to one object in their visual field. And again, if we show them the same one multiple times, they may be presumably attending to, let's say, this one on one trial, maybe another trial, they notice this over here. So it doesn't seem like it's systematic. As long as everything's equally salient, they'll just kind of, attention will glom onto one of these objects. But the important point is it doesn't seem to be able to capture or appreciate all the objects in the visual scene. So you can imagine in everyday life how much of a problem that would be if you're not attending to most of the things that are around you. So it's another one of these very debilitating conditions. And it can occur with lesions, or it can also be degenerative occasionally, like I just mentioned with our patient. And
I have a question.
Yeah, Austin.
So for that patient who was the artist that had the Balint syndrome, did she tell you how exactly it affected her ability to paint? Like,
Yeah.
what did she experience?
Yeah, as I recall, it was a fairly intense conversation, because she was an artist for a long time and she loved to paint, and she just couldn't do it up to her standards. because she just couldn't appreciate the full work of art. She couldn't put together, my sense was, and this was quite a while ago, but I got the sense that she had an image in her head of what she wanted to paint, but she couldn't get it on the canvas.
Got you.
She was just kind of focused on one little thing and could put that together. But then when she
Mhm.
tried to paint something else, she couldn't relate that to the first thing that she painted. Right. So it just ended up being a very frustrating experience for her. And so she said, okay, that's it. I'm not going to do this anymore. So yeah, it was really, it was it was a bummer conversation for all of us.
Yeah, absolutely.
Yeah.
Oh, interesting. Thank you.
But this was, in some ways, it kind of shows how important things like hobbies are to people, because it also affected many other areas of her life. And you can imagine who's going to want to walk down the street if you have this attentional deficit. You may not notice the car coming at you. But she was really focused a lot on having to give up the painting. That was traumatic for her. And that was maybe one of the greatest traumas, even in addition, relative to some of the other aspects of her life that were really curtailed. Yeah. Any other comments? Yeah, and with her, one of the other things that's tragic about this is that Alzheimer's disease and Alzheimer's pathology is progressive. So it's right now we don't even have a good way of getting it to stop getting worse. And so she knew what she was in for. That's one of the things that people with Alzheimer's disease or various neurodegenerative disorders, Parkinson's disease is another one. They can see, where they're headed, and it's not pretty. So yeah, I think that was also part of, I think, her reasoning was that it's just, I can't do this to my standards. I'm not doing it well now, and I'm only going to get worse. So yeah, it was a real tragedy. All right. I'll try to pick it up as we move on with this, but that's the thing. You talk about neurological disorders, and there's a tragedy embedded in everything that we talk about. It's somebody's brain and it's not working as well as it used to, and that's a tragedy. All right. So you can also more rigorously test this idea of, are they really just kind of, is this a spatial issue? With the dots, for example, they're spread out on the screen. So is space the only aspect of their problem, right? So I think we've already established that space is one big problem. Spatial attention is one big problem for these people. But you can also see this if you present two stimuli, one on top of the other, that tries to limit the spatial influence. Just like when we talked about the negative priming before, where we had the dog and the wrench and the pictures are superimposed. So if you give these people with Balint syndrome a task like, okay, judge if you see a word or picture or if both are shown. And so you have different trials where it could be only a word or only a picture. And this is a control. If you show this, the people can see the word and they can see the picture. So again, this is a high level problem. It's not an issue of recognizing words and pictures. But if you superimpose the two, right, you've got the word ruler on top of, this looks like it's probably celery or something. What you get is that on some of the trials, people will notice that that there are two things there, a word and a picture. Right, so this shows that they just it's not as if they can't do the task at all. But you and I, we would get 40 out of 40 for recognizing that this is a word and this is a picture. And these people here, that this is, 40% of the time they get it correct for GK. 30% of the time JF gets it correct. The bulk of the time, they're saying it's just one thing. It looks like the picture may be the more salient feature here. So they're more likely to say the picture. JF on 5 of the trials said just the word. So this is showing that even if you try to put two objects in the same spatial location, if they can be perceived as two distinctly different objects, a word and a picture of something else, they'll attend to only one of them. So that their attentional problems go beyond just space and attending to one part of space or one object in a part of space. But it also seems like this attentional deficit is there for non-spatial selection as well. right? We talked about attention is at its essence, it's about selecting things, selecting one thing at the expense of others. And normally, we're able to select both of these things that are overlapping. With these people, it seems like it's only most of the time, at least the majority of the time, it's one or the other. So one way to think about it is it's an extreme selectivity is one of their main symptoms, in addition to the eye movement and visual guided movement symptoms. And they're all related too, right? The eye, moving your eyes around is important for being able to select visual information for attention. And visually guided movement, there's an attention element to that what you're using in vision is something that you probably attended to guide your movement. So if the attention part is thrown off, then the relationship between the visual information and the movement information is out of register. Okay, so let's talk about the types of lesions that can give rise to Balint syndrome and how that differs from hemineglect. And so generally, one reason why Balint syndrome is fairly rare, thankfully, is that you need to have damage. It seems like you need to have damage in both the left and the right hemisphere. So it's not just a right hemisphere phenomenon, whereas with hemineglect, typically, almost all the time, the lesion is in the right side of the brain. And much of the time it's in right parietal lobe. Probably the number 2 area, just kind of for those that are interested, is inferior frontal gyrus in the frontal lobe. That's probably the second most common place to get neglect. So these are different areas. They don't overlap completely in the parietal lobe. So the Balint syndrome is more kind of a little higher up and more towards visual cortex. And even the bigger difference is that you have lesions on both sides of the brain for Balint's, whereas only one side seems to be sufficient for hemineglect. And this is showing some of the images on a structural MRI, so you can get a sense of how big these lesions are. And so to get some of these, fantastic failures of attention, usually, especially for Balint syndrome, the lesions are pretty big. It's not the sort of thing that would show up with just a subtle lesion. Although there are certainly cases out there for hemineglect where you can have large degree of hemineglect with a relatively small lesion. And sometimes people will have relatively big lesions and not have hemineglect, even if it's in the areas of the brain that we've been talking about. So there's a general correlation between lesion size and the severity of symptoms, but there's a whole lot of unexplained variability behind that as well. All right, and so this just illustrates, looking at MRI, that these are bilateral lesions and they're pretty big. Okay. So any questions about Balint syndrome or comments? Okay, so we're just going to go through and just talk about a few more neuroimaging studies to get at some of these cueing effects in these areas of the brain that are impaired in people with neglect and to some degree Balint syndrome as well. And then also we'll bring in some EEG studies, which we haven't talked about yet as far as this attentional shifting that goes on. So I want to kind of tie these lines of work up together, and then that'll be it for today. So this is just showing that depending on where you place a cue, again in our cue target paradigm, you get these increases in activation in these areas of visual cortex and other parts of occipital cortex. So this is sensory processing areas that show up opposite to where attention is supposed to be shifted. So if you cue people on the left side of space to shift attention to the left versus to the right, you get bigger activations to the cue. So this is before the target shows up. The last fMRI study that we talked about, that was in response to targets. Now we're talking about cues. And the idea here is that this is the spatial cue that asks people to voluntarily, endogenously shift attention in space. And then we want to know, okay, what's going on in the brain when they're presumably moving attention around towards the left side, towards the right side. And the answer here is that you can get increases in activation in visual cortex that maps onto the location where attention has been shifted to. So that's what we see here. So if attention is shifted to the left, then these right sides of visual cortex are showing greater activity after the cue is presented and before the targets. If, on the other hand, we tell people, okay, now we want you to shift attention to the right, now the left side of the brain is the one that's showing these shifts. And have a visitor. And so those same areas, it's as if they're being prepared for the target, right? And then so if you do present the target at that location where attention is oriented, you get greater activations to the target as well. So it's showing this, it's connecting the link between the cue, moving attention to the cue, and then how is the target processed. And the bottom line here is that it looks like these cues can engage sensory cortex to have a greater response if the stimulus is at the location in space where the target shows up. So it was a pretty cool study, and they have this very nice, you can see, you can get really quantitative about these overlapping areas. I mean, this splotch here and this splotch there pretty much look like this splotch and that splotch. But it's not perfect, right? There's a little bit of, activation here in this experiment that we didn't see there. This is the sort of thing where if you run an experiment multiple times, these activations are slightly different. So we could see if this is replicable or not. My guess is it probably wouldn't be, but I don't know for sure. All right. Now, lastly, so we talked about how sluggish the blood flow response is in fMRI. I just showed you that on average, something happens after the cue that seems to engage sensory cortex. If you want to get a more fine-grained sense of what happens over time, because the difference between the cue and the target in these experiments was, about, let's see, trying to remember, it was about a second or so, maybe even a little more. That you can measure something called this biasing related negativity every 100 milliseconds if you want, every 10 milliseconds if you want. It really just depends on how precise you want to get with it. So what you do is you run the same experiment. You have a cue that says shift attention to the left, and we want to measure electrical activity in the brain now that may be influenced by the direction that attention is being shifted. And so what we're looking at here is after this cue, this slow potential develops as the person is shifting their attention in space. And they call this the biasing related negativity, the BRN. I don't think that's really a standard term in the field nowadays, but that's what they use for this paper. And you can see here that there's this negative potential that develops here. That's what the purple is showing. And if you squint real hard, you can kind of see when they attend to the left, maybe there's a little more activity over here on the right. And if they attend to the right, you can see here's probably where you see it best. So there's a little more negativity over here on the left side. What they did here for their analysis was to subtract the electrical activity for these two conditions. And when you do that, then you have a much better sense of, oh, all right, when they're tending to the right side of space, you get this greater activity over left visual cortex. That's shown here in the yellow. And when they're attending to the left side of space, you get this greater activity over here on the right side of visual cortex, and that's shown here in the purple. So this is fairly common in EEG studies and also fMRI studies, is to look for a difference measure to more sharply illustrate that a difference is actually there versus just trying to kind of squint, when you look at the top two rows. So that's what they did there. And this thing develops, after several hundred milliseconds. So once that cue comes on, there's this sluggish lag before this attentional shift seems to take place. And if you recall early on when we talked about endogenous attention, the performance for the cueing doesn't get really good until about half a second after the cue is presented. So these EEG results are more or less in the ballpark with the cueing results that we see behaviorally, that it takes several hundred milliseconds to voluntarily shift attention to a region in space and then get ready to respond better to targets at that location in space. So again, we have some convergent evidence, in this case, at the neural level. So think about Mars levels, right? This is the implementation level with neurons, electrical activity of neurons is telling us that spatial attention shifts take, several hundred milliseconds. And when we think about the algorithmic level, these spatial shifts for valid and invalid targets and cueing effects in general, that's also telling us that it takes several hundred milliseconds for all that to happen. So it's nice when you look at these different levels of description and you get the same basic conclusions. All right. So one last thing, I forgot that I put this in as well. So one last thing, we've been talking a lot about endogenous shifts of spatial attention. And what we just talked about here is electrical activity in response to when you voluntarily shift attention. There are ways to capture attention, and we talked about this as well earlier, which is when you have a pop-out visual search. If you're searching for a red T and something red shows up and it's T, and it's the only thing that's red in the entire visual search array, you have a bunch of other letters and they're all green, you get this pop-out effect. It's just obvious that that's where the red T is, and you know it, and you can press a button fast. And it doesn't matter how many other green letters there are, your reaction time doesn't change very much. So this has captured the imagination of a lot of researchers because they're wondering, what is it about these automatic effects? What's going on in the brain that's associated with automatically picking out something that sticks out in a visual scene, something that's salient? And so what do? Well, let's just have our basic visual search task with pop-out effects and measure the brain activity at the same time. Right, so it's the usual approach. You have your behavioral studies. Let's measure the brain while they do the same behavioral study. And so this is from one experiment. Actually, I don't have the citation here. This is from the book. But one of the main researchers, and this is a guy named Luck, and he was the one that discovered this potential called the N2PC. So the N2PC just means that it's a negative potential here. So here negativity is plotted upwards. So that's what's shown over here, over here, this negativity. And it's in the posterior parts of the brain, so that's where the post P comes from, and it's contralateral to where the pop-out stimulus is. So here, this one stimulus that pops out is the one that has the white filling. So that should elicit an N2PC over the right visual cortex. This one here pops out because it's on its side, and all the other ones are straight up. Again, this is relative to the fixation point. This is on the left side. So we would expect this N2PC to be recorded over the right visual cortical areas. All right, and yeah, and so I didn't give you one of those topographic maps that shows the voltage spread out. I probably should have, but at any rate, just take my word for it. This shows up on the opposite side of the visual cortex relative to where the pop-out stimulus is. So there's been a cottage industry out there trying to study this N2PC as well, because it gives us a lot of information about the time course of when these pop-out effects occur. And here it's showing the pop-out effects start around 1/5 of a second after the stimulus is presented. So that's relatively fast, but it's well after the time when primary and secondary visual cortex neurons first start to respond. But nonetheless, it's pretty rapid relative to behavioral responses, which could be several hundred milliseconds after the N2PC occurs. All right, so let's just wrap it up. So putting together a lot of these different lines of evidence from lesion studies in patients, some of our fMRI studies, and some of these EEG studies. The current model nowadays is that there are these attentional systems in the brain that are distributed across areas of frontal cortex and areas of parietal cortex. And just because of time considerations, we focused a whole lot on parietal cortex, not a whole lot on the frontal lobe. But these systems here that we're talking about here, the dorsal stream, which is shown here in blue. So we've talked a lot about the infraparietal sulcus, superior parietal lobe, and temporoparietal junction here, which is the area that's most commonly when you lesion that's when you get hemineglect. And then there are also frontal lobe areas. One is called the frontal eye field up here, and that tends to go, the activity in these areas tend to go together. So when you're shifting spatial attention around, you can see these activations in inferior parietal lobe, or I'm sorry, the inferior parietal sulcus up here. You'll also oftentimes see that in the frontal eye fields. I didn't show you that data, but it's out there. And when you get some of these hemineglect symptoms, you can have lesions in temporoparietal junction. or the ventral frontal cortex, ventral VFC over here, inferior frontal gyrus, right there. And there's a very nice overlap here between the imaging studies and the electrophysiological studies and the lesion studies, especially the ones that show involvement with neglect. So this is kind of where the field is at now, as far as we at least have a general model of these large-scale attentional systems. These attentional systems can influence sensory processing. So we talked about that a few minutes ago with respect to visual cortex. So the idea is that these are kind of high-level areas that reflect endogenous attention and exogenous attention that can influence how sensory processing works. So it's kind of a nice model that people are working on testing and then trying to get beyond this simplified model, which, you know, if attention were this simple, humans wouldn't be this smart. Our behavior wouldn't be as nuanced and refined. So there's a whole lot more to the story, but at least we have, you know, a set of data that's all kind of hanging together currently. So that's, and this is just kind of showing a schematic of that, of what I just showed you, for those of you that are interested. But the main point, I want to just emphasize this more than the schematic. All right, so I think we'll leave it there. So are there any questions about this kind of higher level attention control unit that we've talked about the past few days? All right, well, there you have it. So let's just end here. We can end a little early today. And I'll see you guys on Thursday.
Thank you.
Bye.